So, before we get into the next step of this, we have to realize our allele frequency, our dominant allele plus our recessive allele is going to equal 1, but we also have our genotype frequencies. There are 3 genotypes: our homozygous dominant, our heterozygous, and our homozygous recessive. The frequencies of each of these added together will also equal 1 when we're looking at individuals and genotype frequencies. This is going to become very important in a minute. So back to our little problem here. For P and Q, what we're going to do is we're going to divide our dominant alleles that we found. Remember, that was 700. Divide that by 1,000 and we get 0.7. And that is our frequency. If I wanted percent, I would take that 0.7 and multiply by 100. Going over to our recessive allele, I take my total of 300, divide it by 1,000, and I get 0.3. That is my Q value. If I take my 0.7 plus my 0.3, that should equal 1. So that means I have the correct frequencies. Okay? So once again, to get percent, you take those frequencies, you take those decimals, and multiply by 100. So I can use expected frequencies to compare my data. And what do I get? I plug in my numbers, my p squared plus my 2pq plus my q squared. And in this instance, my frequencies match my offspring. So my frequencies of my offspring match my parent data. So when the frequencies are equal like this, no evolution of this population. Okay, if I had data from a real population, I would do this process and then I would calculate it out, calculate what I would expect, and then if my values were different, then there would be evolution. But since they're the same, there is no evolution. Let's look at a practice problem. In a problem of 850 mice, so that's my total population, 720 are brown, and brown is dominant to white. Solve for the following. Okay, so 720 are brown mice. They are the individuals. Okay, that means whatever left over are going to be white mice. I want to know the frequency of dominant and recessive alleles in the population. I want to know the percentage of the population that is heterozygous. And lastly, I want to know the number of individuals that are homozygous dominant. So I have 3 different things I want to solve for, and I'm going to walk you through them. It's not really that difficult. This is a typical problem. I could ask you about any recessive disorder in a population. I could ask you about an isolated colony and what happens to a particular allele in that colony. But the steps to solving these Hardy-Weinberg problems are all the same. And I forgot to put in here, but yes, we are going to assume that the population of the 850 mice are, in fact, in Hardy-Weinberg equilibrium. Okay, so here are my totals. I have 850 mice total. 720 of them are brown, but I don't know their genotype. Remember, I was given phenotype. I know they're brown, but I don't know if they're homozygous dominant or heterozygous. And 130 of them are going to be white. Those are my recessive individuals. And those are the ones that I want to start with. Whenever I tackle a Hardy-Weinberg problem, I want to start with my homozygous recessive individuals. This would be my Q square. So I just pull that part out of the equation. I pull out my Q square and I take my 130 and divide it by the total number of individuals. You have to remember what Q square means. Q square means the individuals that are homozygous recessive. Do not confuse this with Q. This is not the frequency for recessive allele, okay? Two different things. We are working with individuals at this point. So I take 130 of my white mice, individuals, divided by my total population of 850, and I get a frequency of 0.153. That means 15% of my population has white fur or is homozygous recessive. So how can I use this information to calculate my allele frequencies? Well, if to get Q from Q squared, I'm going to take my square root of my frequency above. Okay? The biggest mistake I see at this point is people want to take that Q squared value, the 0.153 that I got, and square it again. That is not what you do. You want to undo the square. It is already squared. So I want to undo the square by taking the root. So I take the square root of my 0.153 value, and that will give me Q. And Q is the frequency of my recessive allele. And I get 0.391. Since that is Q, I can plug that into my allele frequency equation. P plus Q equals 1. I plug Q in, and with simple algebra, I subtract 1 from 0.391, and I get 0.609. This is the frequency of the B allele. So when the question asks for frequency, I'm going to leave it in my decimal form. Step part 2, or part B. So now I want to use this equation to solve for my genotypes. I want to break it down. I wanted to know my percentage of heterozygous. So what I'm going to do is I'm going to just pull out my heterozygous portion, my 2PQ, and I'm going to plug in my allele frequency values into P and into Q. And I just multiply. And I get 0.476. Multiply that by 100, and I get 47.6% heterozygotes. I can do the same thing to get my homozygous dominant frequency. It is P squared, so I'm going to square P or multiply it by itself. And I get 37% homozygous dominant of my population. If you take your percentages and add them up, if they get to 100, you know you have the right values. But we need one more step because I did not ask for percentage of my homozygous dominant. I asked for individuals. So to get number of individuals, you have to take your total population, your total individuals in the population, multiply it by my homozygous dominant frequency, that is 0.37. Multiply that, round to a whole number because you cannot have a fraction of an individual, and you get 314 individuals. So you have to be able to apply these equations to a situation like the one I just showed you. However, please, you do not have to memorize the formulas or the meaning of the variables. These are on the formula sheet. Look at the AP formula sheet. They are there. The variables are defined for you. So you really just need to work on applying these formulas. Okay?